Okay, in this video, I'm skipping over 13D. The topic of 13D is the canonical ensemble, which is a nice topic, but in the interest of time, I'm going to skip it and go on to section 13E, which builds on what we were doing in 13C. And the end goal that I have here for this video is I want to prove the Boltzmann equation for the entropy, which was something that we were using back in chapter 3 without proof. And now we have the tools that we need in order to prove it. So from 13C, we had this formula for the average, the mean molecular energy. And so using this formula, we know that the total energy, which I called capital E before, is equal to the number of molecules times the average energy. And this is just a rearrangement of the definition that I used to find the average, which was the total energy over the number of particles. And again, the ground state energy may not be zero. For example, the quantum harmonic oscillator, the ground state is not zero. Okay, so there are some systems where the ground state is not zero, in which case we need to shift the mean. And I'm going to do that here by talking about the total internal energy of the system. So I'm going to let the total internal energy of the system equal, at some temperature T, equal the energy when only the ground state is occupied. Okay, that's what U of 0 is. Only the ground state, which is what you would expect if the temperature was 0. Hence the reason it's written U of 0. Okay, so the internal energy is going to be the ground state energy, where each state is in the ground, or each molecule is in the ground state, plus this total energy above the ground state. All right, so into this formula, I'm going to plug in my expression for the mean energy. So I've got U of T equals U of 0 plus N mean energy. The mean energy has a negative sign, so it's going to be minus N over Q times the derivative of Q with respect to beta. So this is my formula for the internal energy, U. And again, here we can compute the internal energy if we just know the partition function. And remember how we get the partition function? We sum E to the minus beta epsilon for all energy states epsilon. So if we have for example, a complete quantum picture of a system and all of its energy states, we can compute Q from that. And then we can use that to compute things like average energy and internal energy and many more things that I'm going to get to in just a minute. And for the sake of completeness, I just want to point out that we can do the same thing we did before. We can write this in a slightly more compact form as the derivative of the natural log of the partition function. All right, so now we have everything we need to derive the Boltzmann formula for the entropy, which remember was this formula, S equals K natural log of the multiplicity, which we were using back in chapter 3. I stated it without proving it, and now we're going to derive it. Okay, so to start with, remember the total energy of the system. We had a couple different ways of writing it. We can write it as the number of particles, molecules, times the mean molecular energy. Another way we can write it is as a sum over all the energies, epsilon I, times the number of molecules that have that energy. So using this second version, I can write the formula for U of T, which equals U of 0, plus the total energy, which earlier I wrote this way. Now I'm going to write it this way. Okay, now I want to find du. And so what could cause a change in U? Well, the energy levels could change. So change in U could be due to the energy levels shifting by some amount d epsilon I, or if the populations change. So maybe the populations in I shift by some amount d in I. So when I take the differential of du, I need to incorporate both of these possible changes here. Okay, so du is going to equal u0 is a constant. Well, okay, let me come back to that. So du0 plus, now I need to use the product rule. Okay, so I need to use the product rule on this. So I have the sum of d epsilon I ni plus the sum, whoops, ni is supposed to be up there, plus the sum of epsilon I d ni. And so both of these terms equal 0 if the volume is fixed. And if you think back to quantum and the quantum harmonic oscillator, you know that the ground state will change if you change the size of the box when you have a oscillator in a box. But as long as we're not changing the size, the ground state is going to be unchanged. And the same with the energy levels. The energy levels are not going to change as long as we keep the volume fixed. Okay, but the populations could change. So the number of molecules in the various energy levels could change. Okay, so that simplifies this formula quite a bit. So I'm going to write the simplified version now. Okay, so du is equal to the sum of epsilon I dni if the volume is fixed. And going all the way back to section 3e, we had this formula. Du is equal to T ds minus P dV. So we called this equation the fundamental equation of thermodynamics, and you can find it on the page 52 in the notes. Okay, so continuing with this fixed volume, if the volume's fixed, then dV is 0, and so du is equal to Tds. And so now I can write a formula for ds using this formula for du. So ds is du over t. And du is this. So I have 1 over t times this sum. And to get beta into the formula, remember that, so if I take 1 over t and I multiply it by k over k, I get k over kt. And beta is equal to 1 over kt, so this is equal to k beta. Okay, so I want to use that for 1 over t. All right, and now we're going to make use of an equation that we arrived at while we were deriving the Boltzmann distribution. It was one of the intermediate equations. And that equation looked like this. And this is the equation we arrived at when we were using the method of Lagrange multipliers. And so you can see where this equation was derived. If you look back at page 128 of the notes, I called this equation solution, because it was the solution to our max-min problem, where we were trying to maximize W. And since we were maximizing W, that means that this is true for the most probable configuration. But as we pointed out, the most probable configuration is so much more probable than every other configuration that it's the only one really that the system can be in. So this is the only one worth considering. So it's the only one worth considering because it's the most probable configuration, or the most probable configuration is so much more probable than all the other configurations that the system will always be found in this configuration. Okay, so we're going to use this, and we're going to solve it for this term, beta epsilon I, which is simple. We just add the beta epsilon I over to the other side, and we end up with this. All right, now looking back at the formula we had for ds, it was k beta times the sum. Beta is a constant. I can move it in and out of the sum. I'm going to go ahead and move it into the sum so that it looks like this. And now inside the sum here, you see that I have beta epsilon I, which is this. So I'm going to put this in to the sum. Okay, so, oh, and can't forget my d and I. And now this is the sum of a sum, so I'm going to split this into two sums. And I end up with something like this. I factored the alpha out of the sum because it's a constant. And notice this term. This term is effectively, since n is the sum of all ni, then this is effectively dn, the change in the total number of particles. Well, the change in the total number of particles is 0, since the total number is fixed. And how about this term? So this, if you remember our definition of the differential, it was the sum of the partial derivatives with respect to each of the independent variables times the differential of that independent variable. So this is actually the definition that we wrote earlier for the differential. In this case, it's the differential of natural log w. Okay, we're really close now. So this term was 0, it goes away. And this sum turns into the differential of natural log w. And so now let me make those changes, clean this up. So everything has simplified down to this. And you see I have a differential on both sides, so I'm going to integrate this. And I need to be a little bit careful about integrating it and thinking about what the bounds of my integral are. But it's pretty straightforward, so I'm just going to jump to the punchline, which is if I integrate both sides here, this differential becomes s, k is a constant, and this differential becomes natural log w. And this is the famous Boltzmann formula for the entropy using a microscopic description for the entropy, which comes from the multiplicity function. Okay, so we've come full circle. We were using this back in chapter 3, and now we have derived it, and that's where I'm going to stop for this course. There's one more thing that I just want to mention, which is some of the other uses of the partition function. So if we have the partition function Q, which we do if we know what all the energy states are, and we may know this from basic principles in quantum mechanics. We may know what all of the energy states are, and we can use that to calculate Q easily as a sum over these. And if we know Q, then we can calculate many things. We saw these three already, so you can calculate the population fraction that's in state I. That was in section 13b. You can calculate the internal energy and the mean molecular energy. Those were in 13c. You can also calculate from Q, you can calculate the entropy, S. And while I derived the Boltzmann formula for the entropy, which is in terms of the multiplicity, you can also find the entropy in terms of the partition function, which is also done in 13e. But I omitted that part. And there's more. You can calculate the Helmholtz energy from Q. You can calculate the pressure of a gas. And from this, you can derive the perfect gas law, you can calculate the Gibbs energy from the partition function, G, and you can calculate the equilibrium constant that we saw in the last chapter, K. So all of these are done in 13F, which we're not going to have time to get to this semester. But if you're interested, you can find the derivation of all of these from the partition function in 13F. So to summarize then, if you look at this list, you can see that we have more or less, we are able to recreate effectively all of thermodynamics. And we can do that if we know the partition function. And this is the essence of statistical thermodynamics. It's starting with a partition function and using that to compute everything that all the thermodynamic variables that we want to know. So it's a very powerful subject. It's very elegant. The math is not easy, but it's very elegant, and really I think it's a beautiful subject. So and anytime you have this much power from a basic idea, then that is worth remarking, in my opinion. Okay, so that's where we're going to finish up this semester.